hopefully some of you have already started or are done reading the reading assignment. And so a lot of this stuff should potentially look familiar, hopefully look familiar, but we're just going to go through it. The first thing that I think your book does, so we're talking about statistics now. Ready? Okay. Just ask. Just want to make sure. I'm not trying to be a jerk. If you're not, we can talk about it. Okay, so the first thing, when people hear the term statistics, we're going to study statistics, and Naked Statistics talks about this a lot too. People have a tendency to kind of freak out, and they get overwhelmed before they even try to understand what the hell is going on. Two important things. One is, this is not a statistics class wherein I am concerned with you being able to hand calculate formulas and know where formulas come from and those types of things. What I want to be able to do, or what I want you to be able to do, is look at a paper, like the one we're going to read at the end of this week, or the one that we read last week, or the ones that we're going to read heading into the future, and be able to interpret the statistical analysis that they used and understand the strengths and weaknesses with those statistical approaches so that you can better interpret and discern information. And this is kind of the whole point of Naked Statistics, which is that stats is all around us. We're always being bombarded with statistical information, whether we realize it yet or not. But the more we become aware of it and the better grasp we have on understanding it and being able to better interpret it, the better off we're going to be in terms of program evaluation and assessment and those types of things. So the book does a really nice job. This is one of the reasons why I like this textbook. It does a really nice job with taking a step back and saying, this is not a statistical cookbook. What we are doing is trying to understand statistical concepts. And when there are formulas, which there are a few in this note set and there are a few in the book, you don't need to memorize those formulas or know how to work those things out by hand. But what you should be able to do is understand when you're interpreting different statistics, what those concepts are, what's being applied, what should have been done, what the most appropriate thing to use under a particular time in certain circumstances, etc. Okay? So, now, I would encourage you all to take, for the exercise science major, you have to, one of the electives is either Stat 327, which is more of a psychology course, or you can take Stat 243. It's been recommended to me by people in the stats department to consider taking Stat 243 along with a stats class called 352. And those two classes together basically spread Stat 327 over an entire year and really present statistics in a way that's understandable and applicable. Right? So for those that are going into medical professions, those two classes can be really useful. Even though Stat 243 is all you need to get into like PT school and different things like that. Now, one of the things that we're gonna read a program evaluation, assessment and evaluation at the end of this term, looking at a continuing education program in physical therapists. And the number one thing that doctors of physical therapy that are in the field practicing right now say they wish they had known more of is statistics. And it's the thing they feel that PT school and their undergraduate education, it's the one thing that they feel like underprepared them to be able to read, interpret, and understand results. So how we're going over this information and how we're going to dig into the articles actually have a lot of implications moving forward, not just this term, but as we continue throughout your career here and beyond. All right? So this is important stuff. Well, I would argue that it is. Okay. Basically, why do we use statistics? We use statistics to turn data into meaningful information. So a jumble of numbers together, in and of itself doesn't provide us with a lot, but if we start to look for meaning in those numbers through statistical analysis, then those numbers begin to give us information. When numbers mean something, then we can use that to make assessments, right? So this is statistical, the statistical revolution, for instance, in a sport like baseball is something that Moneyball is talking about. And what they found was that, yes, batting average is a statistic, but batting average is probably not the best statistic for determining the skill of a hitter, right? Because the way batting average is calculated, it doesn't take into consideration walk, it doesn't take into consideration the situation, it doesn't take into consideration how well the person is hitting when runners are on base, it doesn't take into consideration if the batter is hitting the ball hard, but just is having bad luck and hitting it at people. It doesn't take into consideration if the batter is not hitting the ball well, but they're in a lucky streak where they're just finding open spaces and getting easy hits. And so now this is one of the things that they've done is started to understand how to use stats to get meaningful information instead of just a number that then they're over-interpreting, right? So now when they look at somebody, or when you look at a batter that is hitting uncharacteristically below their average, typically when you look at what are called the advanced metrics, you can see whether or not they are just getting unlucky, whether they're hitting the ball hard, and all these types of things. And baseball works really well for this because of its controlled nature and its huge sample sizes. Regular players bat 4 to 5 times a game, 3 to 5 times a game, and they play 162 games a year. So you have a large, what's called statistical sample or power to pull from. Okay? So meaning from data. And we need to use this for everything. Okay? So again, going back to last Friday's article, they wanted to find out by doing a needs assessment whether there was an issue with the physical therapy being provided to stroke victims. You take those stroke victims and you gather survey information and other data, but then you have to turn that data into meaningful information, and you can do that through statistical analysis. Okay? Now, there's a bunch of different levels of measurement we're going to start from the simplest, going up to the more complex, and actually more usable and more meaningful. But nonetheless, statistics come in a large kind of, all shapes and sizes, if you will. So the 4 main levels of measurement that you need to be familiar with: nominal, ordinal, interval, and ratio. The nominal level is simply descriptive or attributes or properties. So things like using numbers to delineate different players on the court, right? So a jersey number, a highway number, a locker number, these are statistics in a way, but we're just using numbers to assign an attribute. But it tells us we can't really do anything with those numbers. We can't average jersey numbers on a basketball team and get any usable information, right? But you can say, particularly in football, certain number. It's not as kind of tradition would suggest that usually different positions have specific numbers. That's the way it is in rugby. It's similar to how a lot of times that's the way it is in soccer as well. But there's no you can't do any statistical analysis with that, but it is a useful stat. So the ordinal data is interesting just in the sense that it gives us the ability to say more than or less than for a given quality or attribute. So these are things like percentile ranking, right? So if a person scores and you say they scored on the ACT in the 90th percentile, then all you can say about that individual is that their score was higher than someone in the 85th percentile. But it doesn't tell us if those percentiles are differentiated by 1 question, by 10 questions, by huge amount. It just tells us where they are. And it also only tells us where they are within a certain population, right? You wouldn't say that you can't compare your percentile ranking to the SAT to like an 80-year-old, right? Because the 80-year-old isn't under the same circumstances of being drawn from the same population. Again, it's a ridiculous example, but okay, so another form of ordinal data is simply rank assigning. And rank assignment can be really useful because you can start to basically just see how people fall within a particular range. So if you just randomly had these scores based on something, you rank them in order, that's useful because we know that one is more than the other one. And then you can assign them a rank, first place, second place, third place, fifth place, sixth place, seventh place. Does that make sense? That's it. These are examples of ordinal data. Okay? Intervals, or interval data, is kind of the next step beyond the ordinal data, meaning that we can, there is a 0 point on the scale, and the difference between 1 and 2 is equal to the difference between 2 and 3. So each step in an interval scale is equivalent. Does that make sense? So we already said that if you're in the 95th percentile in the SAT and somebody else is in the 85th percentile, it doesn't mean that you had a difference of 10 points on your score. You can't make that assumption because each one of those percentiles is not attributed the same difference. So the classic example for interval is temperature. So if you look at temperature like the Fahrenheit scale, if you have a temperature of 0, it does not mean the absence of the attribute. That 0 has meaning, right? It doesn't mean there's no temperature. Does that make sense? This is a really important point. But the change from going to 0 to -1 or 1 or 0 to 1 is going to be the same difference, either warmer or colder. Right? So the intervals are the same. There's a 0, but the 0 is what's called arbitrary. It's just there. And it has a characteristic. So we know that when people say it's 0 degrees outside, we know that means that it's cold, not that there's no temperature outside. Okay, that's important. Okay, and then the ratio level, which is where we're going to spend the majority of our time, it's the most precise and useful because you can make specific statements comparative statements. So you could say things like twice as much, or half as fast, or half as much. Those things have meaning. Okay? And we can run statistical calculations on these because comparative statements can be made. Right? Okay. So, what do we do once we have these different numbers? How do we order them? How do we work with them? How do we mold them into what we want? And so we're going to talk about some different ways to take raw data, which just means like you did some sort of measurement, you did some sort of test that was based on some sort of measurement, You collected that information, now you have that information, and you need to use statistics to apply meaning to that information. All right? So one of the first things that you can do, and the most basic things that you can do, is rank things in order from highest to lowest or lowest to highest. So if you have body fat percentage in this example, you simply order those, and then you look for the frequency of certain characteristics. So there's 2 at 13, there's a couple around 20 and 21, there's some between 25 and 30, and you can begin to organize data in a way that can be used to find out how people rank within that group. And if you have data sets that are large enough, you can rank it back to an entire population, right? This is where standard scores come from. So, you know, when you do the president's physical fitness test in schools, and you do how many curl-ups you can do in 1 minute, there's certain percentiles where you can take your raw score and compare it to other scores within a population and find out what percentile you're in. And that's based on distribution data across everybody. They didn't say, well, the 100th or the 99th percentile is 100 curl-ups, and the 1 percentile is 1 curl-up. And that's how we're going to set the percentile rankings, right? They collected all the data first, grouped it, and then you create the percentile ranking. Does that make sense? All right. So if we take this, this is a simple frequency distribution example. N is the total number of subjects. So in this case, we have 100 subjects or 100 students that participate in this test, or 100 participants in the test. So N equals 100. And then you rank the scores from, that's embarrassing. So you rank the scores from, or you arrange the scores from highest to lowest. But instead of writing 45 twice, you simply say that 45 occurred 2 times. And that's its frequency. Right? So only one person did 58, one person did 55, one person did 54, etc. 4 people did 40. The most common score was 34. Right? And now we can start to begin to understand maybe some characteristics about this curl-up test and the population that's doing it. Right? So we can start to say, oh, well, 34 is probably pretty close to the average, for example, because it was the most frequent score, potentially. Right? Or maybe if you had a class with a bunch of people that were extraordinarily fit, then the highest frequency would be up here, but that wouldn't be indicative of what is normally found when you test the population. Okay. So a simple frequency distribution is one where you list every score and the frequency that's related to that. A really simple way to organize data to get a better idea of what's occurring is to group them into different categories. Right? And we talked about this with the FIM scores. Classification, grouping, so that you can better interpret the information. Right? So you have a group that's 55 to 59 curl-ups, 50 to 54, etc. And then you group these by frequency. And instead of the highest number being 7, now we have the highest number being 24. And this number 24 also coincides with kind of higher numbers that are in the individual frequencies over here. So it makes sense to group these together and get a better idea of where the majority of people are falling. And the majority of people in this data set are falling between 20 and 35 curl-ups in 1 minute. And you can, if you did this on 200,000 8th grade students, you can get an idea of what the middle characteristics of those 8th grade students would be by putting them into these groups and looking at their frequency. Okay? Now, one of the things that you can do to graphically represent these numbers in frequency is to chart them on what's called a histogram. And histogram is a really important tool. One of the things that I want to make sure is clear here, first of all, whenever you read a data set, you have to orient yourself to the graph or the figure. So we see that on the x-axis, we have the number of curl-ups done in 1 minute. And each of the hash marks is separated by the range in the groups that we just identified. All right? So 5 to 9, 10 to 15, 15 to 20, etc. So you get that, 15 to 20, 20 to 25. Then you look at the y-axis, which is frequency, not number of pull-ups. So a lot of times when we look at bar graphs, we just automatically assume that the height of the bar graph is depicting the result of the test. But when you're doing frequency distribution and you're making a histogram, it's not a typical bar chart, it's a histogram, which means it's showing frequency. Does that make sense? So instead of doing curl-ups here, we have frequency, and we see visually what we could interpret in this when we group them, which is less people at either of the extremes and more people in the middle, right? And you all have heard of this before as normal distribution. Right? So this is used all the time when you're curving or when you're looking at the characteristics of a class test score. And you say, oh, well, the average, so just plug in down here instead of curl-up tests, it'd be grades. And you would say, 50 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 100. And then you look at the frequency within each of those, and you get a curve. And depending on where the peak of that curve is, gives you information about the quality of the student, the quality of the test, the level of preparedness, and whether the test was too difficult, properly difficult, or too easy. Right? So histogram is very, very important, and it's very useful in a lot of realms. Okay, questions on this? Wow, such a good at explaining histograms. So another kind of version of this to show the curve instead of the bar graph is called a polygon. And a polygon is the exact same x and y-axis as the histogram. But instead of carving these blocks in and saying things like, okay, well, between 30 and 35, there were 24. And between 35 and 40, there were, 21. Now we just put a dot right in between 30 and 35 and say that there were this number of people that got this score in the curl-up test. And then you can link those together to kind of get an idea about distribution and about a curve. And so a lot of you have heard of things like a bell curve, and a bell curve being normal distribution. And the reason why a bell curve is normal distribution is because the majority of the scores end up in the middle. And as you get farther and farther towards the extremes of that test, there's less and less people. So there's less people that do really bad, there's less people that do really good, there's more people that do average. Normal distribution. Okay? There's other ways, and we're going to learn how to interpret these things a lot better. Tables, charts, pie graphs, bar graphs. Now, a bar graph is different than a histogram in the sense that you're actually looking, the bars are representing the thing that you're measuring, not the frequency of the thing that you've measured. So in this case, you're looking at points per game, and you're just trying to look for discrepancies between points per game. It's just a way of arranging it. So something happened here in game number 6 where the points per game were much lower than any other game. And depending on whether that was a win or a loss, you can look at things like, was it our offense? Was it our defense? Was it our, right? You can begin to ask useful questions, and this is about as simple of a thing as you could possibly do. It's just bar graph the differences. Okay, so back to histograms to a certain degree. We want to understand the concept of normal distribution. And as I referred to when we looked at that histogram with the curl-up test, that was, even though it was a small number of subjects, only n equals 100, they were normally distributed. And so one of the things that you can think about when you're selecting individuals to study, or you're looking at your classroom, your PE classroom, or you're looking at your classroom where you're teaching, your health class, or whatever it is that you're doing, you have to ask yourself, is this subject or is this subset or is this class representative of a normal distribution where other statistics are being generated from? So can you take the characteristics of these individuals and apply it to a normal distribution, or assume that they're normally distributed? Right? So if you are PE teacher at some sports academy for only Olympic hopeful athletes, that's not going to be, you're not going to compare those individuals, their athletic or their physical fitness performance, you're not going to compare them to normal population distribution. Their percentile rankings aren't going to matter, right? So you probably have to take that class as a unique subset and create your own characteristics for that within that class. Okay. Now, normal distribution is characterized by this bell curve, which has the majority of scores in the middle, less scores as you get farther away from the middle. However, we can get a lot of information just by looking at the shape of the curve and evaluate either the measurement or the program or what it is. And this is part of that program evaluation that we went over last week, where you make assessments, you make interpretations, and then you go back and change standards, for instance. Right? So, for example, if the distribution of scores in this class, ideally for you all, would be for it to be skewed negative, which means that the majority, remember, we're looking at frequency here, not test score or not average score. We're looking at frequency. It would mean that the majority of people in the class are above an average grade. So if this X here was 70% overall in the class, we want the majority of people to be above that. We don't want people to be equally below that and above that. Does that make sense? Now, if I just say, everybody stop coming to class, here are all the answers to the tests, here are some things, and everybody gets 100, we would get a skewed negative result, to be sure. But would that suggest that everybody truly understands and learns this material to the same degree and to an effective degree. Right? So this is where you can get kind of thrown off with statistics. Right? On the other hand, we all have heard of like different classes and different things like that where the average of a test score is a 50 or a 60 or something like that, right? And we know, just based on interacting with young people at this level of learning, that the majority of people are not like incapable of learning things to that degree, right? So you can get a lot of information through analysis based on how people are responding. And you can find out how people are responding by taking some sort of validated measure and then creating a frequency distribution and looking at the characteristics of that. Does that make sense? All right. I always, always, always ask the question on the first exam, what is the ideal distribution for students' grades in EXS 312? And 50% of people miss it every time. And I say the ideal distribution for you guys is skewed negative. I'm telling you right now, I'm going to put it on the test and well, I don't know. Maybe people are catching on now, but skewed negative. Right? So they can be flat, they can be tall. This would suggest that there's too much of a spread of scores. This would suggest that the scores are too tight. Depends on what you're looking for. Okay? So these are really important concepts. Now, because we understand that ratio data, we can make comparative statements and we can compare ratio data between subjects. We can also compare an individual's raw score to other characteristics of the entire data set to see where that individual falls within a population, within a class, within a team, within a league, what have you, right? And these are what are called measures of central tendency. So measures of central tendency is where the majority of the statistical analysis that we're going to discuss this term lies. And measures of central tendency allow a score to be compared with a group of scores. So you can take one individual score and fit it into the context of a different population. Right? And we do this all the time. Right? Where do I rank in the conference? Where do I rank on the team? How many goals did I have? How does that compare to the highest goal scorers in the country? Well, how hard are their conferences? What are their schools like? What division are they in? Right? We make these comparisons all the time. We're just formally learning how to think about them in ways that can be applied in a much more useful way. Okay? So measures of central tendency allow a score to be compared to a group of scores. Couple things within measures of central tendency. The two most simple things that we need to learn are the mode and the median. The mode is the score that occurs most often. Right? So if we go back to our pull-up data set, 34 is the mode of this data set. And typically the mode is somewhere in the middle of the curve because it's going to be reflective of where most of the people are, which is going to be reflective typically of average. Okay? Median is just the middle score once all the scores are lined up. All right? So if you have 100, if you had if you have the frequency distribution in the 100 scores, you take the 2 middle scores and average those, and that gives you the median, right? If you have five measures, you take that middle number, you take number 3, and that's the median. So the median is just the middle number. And the reason why median is useful, and Naked Statistics does a really good job describing the difference between mode, median, and mean. And if you look at median, the example they use is Bill Gates walking into a bar where 9 middle class guys are drinking beer. And then somebody makes the statement, did you know the average income of the 10 guys in that bar is like $250 million a year or something like that? Obviously, that statement is correct, but is not representative of that data set. And if we looked at the distribution, we would see it a really high bump for one person. Sorry. It would be very, very small for one person, and the majority of people would fall in the middle. So under those circumstances, if you were to rank them from Bill Gates to the person making the least, the middle characteristic would be much more representative of the true central characteristic of that data set than if you have what's called an extreme outlier. So it may seem kind of silly, like why would you just rank things and then pick the middle number? It seems completely arbitrary. But a lot of times, especially if you think the distribution is normal, then you can find out about the central characteristics by choosing the middle number. Right? Now, the most common is the mean, which is the numerical average. And you guys should be able to calculate this, right? You just add up the scores and divide it by the number of subjects that contributed to those scores. Right? So when we say batting average is a mean. You're just looking at the number of hits divided by the number of at-bats or opportunities to hit. And you get an average, right? So the mean, never mind. That wasn't a great example. But the mean, basically, you take all the scores, divide it by the number. That gives you the average. We all know how to do that. Now, one of the things that is really important that needs to go with average is variability. And variability is this concept of the spread of scores around the average. So, for example, in the Bill Gates walks into a bar example, the average might be 250 million, but if we also report variability, it's going to be a huge number that's far beyond the average, showing that there are some serious outliers. So one of the things that we can get out of a data set when we're given the average or the mean, and then we're also given a measure of variability, which typically comes in the form of standard deviation, we can see how alike the scores were that made up that average. So something with a low standard deviation is a data set with low variability, which can oftentimes represent, and this is, assuming that it's normally distributed, right? So variance is basically the spread of scores around the mean, which is a little bit, variance is the spread of scores around the mean. And standard deviation is the square root of the variance, which tells us how far away from the mean under a normal curve the range of scores is. Right? It'll make sense in a second. So, if we look at where if we look at a normal curve, in a perfectly normally distributed data set, the mean, median, and mode are going to be in the middle. And as we move away from standard deviations, if this score is 0, this is 1 standard deviation, 2 standard deviations, 3 standard deviations. It means that we're moving a certain percentage outward towards the far reaches. And it shows the spread, where the spread of scores occurred along this curve. So in the Bill Gates example, the average is going to be here, and Bill Gates is going to be so many standard deviations away. Because, and this is not a small point, this black line never gets to 0, right? It just keeps getting closer and closer and closer and closer and closer. And so you take Bill Gates, and his standard deviation is way, way, way outside of the mean. Does that make sense? So real quick, I want to show you this example. If we look at mean and standard deviation using Excel, or in this case, Google Sheets, if we put in equals average, we get 5.94. Here, if we put in equals average, we get 5.94. But just looking at these scores, we can see that there's a difference in the variability or the spread of those scores around the mean. So the average is exactly the same. But if we look at standard deviation of these scores, we see a very small standard deviation compared to the average. Whereas here, we see a much larger standard deviation. Because the range of scores spreads a lot farther out away from the mean along that curve. And so higher standard deviation means greater variability and makes it. And this is important because when we want to compare one group to another group and say that, you know, this group that took caffeine ran faster than this group that didn't, and we want to compare the average, if one person is a super high responder, it may look like that average is a lot higher than the average over here, when really it was all due to one person. And that's variability. And so if you have a mean, if you have an average that's significantly higher in the caffeine group than over here, and the variability is low, now you can say something about the effect of caffeine across an entire population because there's low variability. There's similarity in how people, on average, responded to caffeine. Super important. So when you read the paper that we're going to talk about on Friday, make sure you pay attention to the tables that report mean, standard deviation, and think about it in the context of the population that they're looking at, and see how it compares when they're comparing different subjects and different students across years, across grades, across schools. Okay? And we'll begin to understand why it's important to learn to use statistics to give numbers meaning. Okay, cool.